Good evening. It's wonderful to see all of you tonight. Ohio's Frontiers in Science Lecture Series was established in 1991 by a gift from Jeanette Grasselli Brown, an Ohio alumna and former university trustee, and her late husband, Glenn R. Brown. The series features scientists who've been recognized for their commitment to share their scientific knowledge with individuals of all ages. Tonight, I'm delighted to introduce our Frontiers in Science Lecture Series speaker for the evening, Dr. Janna Levin. Dr. Levin is the Tao Professor of Physics and Astronomy at Barnard College. She earned a Bachelor of Arts in Astronomy and Physics with a concentration in philosophy at Barnard College and a PhD in theoretical physics at the Massachusetts Institute of Technology. Levin was also the first scientist in residence at the Ruskin School of Fine Arts and Drawing at Oxford, with an award from the National Endowment for Science and Technology and Arts. Dr. Levin's research focuses on theories of the early universe, chaos, and black holes. She's contributed to an understanding of black holes, the cosmology of extra dimensions, and the gravitational waves in the shape of space-time. She is also Director of Sciences at Pioneer Works. She was recently named a Guggenheim Fellow and is the author of 4 books. The title of her talk tonight is Black Hole Survival Guide. Please welcome Dr. Janna Levin.
Thank you so much for having me. I considered wearing my winter coat during this presentation. We'll see how I do without it. And I was also very mesmerized by the sign language. It's nice to have an interpreter here. I'm really honored to be here. Thank you so much for coming. I talk about some of the craziest, weirdest ideas, and I will give you a little bit of a tour of my most recent book. But we're a pretty small group. I know we're going to do a Q&A afterwards. So I hope people will ask questions and be inspired by some of these ideas. If you haven't seen the book yet, I wanted to hold it up just to show you how wee little it is and how to brag about how proud I am that I made it so small. Do you know the Mark Twain quote, "I didn't have time to write you a short letter, so I wrote you a long one instead"? So this, I spent the time to make this short, and it was really quite an experiment. It's being held up here by the artist Leah Halloran, and it's one of my most favorite projects because of her contribution. She wasn't really as an illustrator. She was a very good friend of mine, and she did a series of 20-some paintings, original paintings for the book. So you'll see those as we talk. Some of the images you can tell were painted by Leah. Oops, that's not supposed to be there. Excuse me, I think we're in the wrong talk. I don't know how that happened. Don't read my messages. Okay. Yeah, I don't know how that happened, but that was one of Leah's paintings. It's cute, right? So here's Leah, and I wanted to distinguish as we go along. You will see some of Leah's paintings. You can tell that they're paintings. And unless I say, a lot of these pictures I'm going to show you are actual observations. Now, here we are on Earth, lovely little planet. We talk a lot about trying to save this planet, preserve this planet. Everything we know about the cosmos, we have acquired from this little solar system. We have never been able to get out of our own galaxy. That is presently still utterly inconceivable. The furthest object that's ever been human-made to travel from the Earth are the Voyager missions, and they only in recent years broke out of the sun's influence. But this is nonetheless an actual observation of our Milky Way galaxy. It is observations made from our location in the solar system and then reconstructed to the best of our understanding in a 3D digital map of where everything belongs, all the gas, all the dust, all the stars. There's some 300 billion stars in our Milky Way galaxy. And out here in Athens, Ohio, you have a better chance of seeing the Milky Way than I do in New York City. But when you see it, it's that milky rift that just passed out of the field of view. And it looks like that because we're inside the Milky Way, precisely because we can't step out. So it's like looking on the edge of this beautiful plane. And here's our ordinary star, the sun, and we're, of course, the third rock from the sun, our beautiful little Earth. And everything we know since the time, really, of Galileo has been brought to us by light across the incredible expanse of space. And I really do mean light. We have some other things. There are neutrinos and some particles for purists out there. But by and large, almost everything we know about the universe has traveled to us through light, and we sit here on Earth. Maybe we have some satellites that orbit the Earth or go into distant orbits, beyond the moon even, or around the sun. But this is where we live, in this particular solar system. And we travel with this solar system in an orbit around the center of our entire galaxy together. Now, this is also an astronomical observation. Everything you are seeing here is itself an entire galaxy. Each one of these is hundreds of billions of stars. And they fill the cosmos literally as far as the eye can see. The universe is 14 billion years old, and since that moment of the Big Bang, as accurately as we can place it, the universe has expanded and grown to be at least 92 billion light years across. There are as many galaxies in our observable patch of the universe, the patch that light has made it to us since the Big Bang, as there are stars in the Milky Way, hundreds of billions. And yet, what I think is most fascinating, maybe I'm being a little bit contrarian here, is all that we cannot see. 95% of the universe is in a form of either dark matter or dark energy that nobody ever has or ever will see. And that's quite amazing, even the fact that we can deduce that. So 5% of the universe, everything you're made of, everything anyone has ever seen or ever will see, is a tiny bit of ash left over from the Big Bang, a tiny bit of residue in comparison to everything that's out there. Now, my favorite in the dark sphere is possibly not making up that much of it, but are the black holes. And that's really what I want to talk about today. If I come back someday, I hope to talk to you about dark matter and dark energy. But for now, let's talk about black holes. And what's most stunning about black holes, their name was only coined in 1967, but the idea was already 5 decades old by then. And the expression black hole was just thrown out, apparently in a lecture when somebody was exasperated with repeating this technical phrase of unhindered gravitational collapse. And someone from the back shouted in this lecture, "How about black hole?" And apparently the name stuck. But the idea of a black hole is that it is the darkest phenomena conceivable in the universe. Black holes emit no light and they reflect no light. And so we're going to take a little bit of a tour of my favorite objects, black holes. But first, I want to introduce the concept of curved space-time, and I'm going to do so naturally with a music video, because why not? What else would you do with? There are the entire idea that Einstein had to replace gravity with a theory of curved space-time is so challenging, so hard to grasp sometimes. And he himself famously struggled with the mathematics. He talks about being unable, writing down wrong theory after wrong theory, and not being able to formulate it right. But the actual intuition can be thought of in 2 simple steps, and that's what I really want to try to do. There's 2 simple steps that go into Einstein's enormous leap that gravity is a curved space-time. The first one is an idea of weightlessness. free fall. So right now you're in your chairs. These guys here, they're on a plane, they're in their chairs. You think of gravity as this heaviness in your chair. That's usually how we experience it, or the heaviness of our feet on the floor, or in an elevator, the weight of your feet on the floor. But the flaw with all of these examples is that a chair is involved, or a floor is involved. Why can't I just think of the gravity of the earth in the absence of these things? So Einstein had what he called the happiest thought of his life. He imagined, I don't actually know if he imagined the elevator, but let's us together. Imagine an elevator. You feel heavy on your feet. Now you cut the cable. What do you think happens to you as the elevator falls? Do you stand on the floor? You actually fall with the elevator. You would look completely weightless. This idea that when I remove the elevator, when I remove the chair, when I remove the floor, that's the purest experience of Earth's gravity. That is falling freely in the gravitational field of the Earth. So I'm going to show you this video. I'm going to tell you what's going on here. These guys are about to film a video. There's no CGI. There's no animation. It's 100% real. They're in a plane, and when the plane is flying upward, resisting its natural urge to fall freely around the Earth's gravitational field, they're pinned to their chairs, just like you're pinned to your chairs. But then the plane literally drops into free fall. So let's watch what happens when it drops into free fall. Anybody seen this before? It's like the greatest video ever made. So the plane's flying, and as soon as it drops, you'll notice. Upside down and inside out, and you can feel it. Upside down and inside out, and you can feel it. Don't know where your eyes are, but they're not doing what you said. So next time your flight starts to drop, you can dance. But you're better off without it. Let's give it one more second, because it's so great. I won't play the whole thing. I could just sit here and watch it with you. That is a real demonstration of what happens when there is nothing between you and the Earth and you are allowed to fall freely. You experience weightlessness. You float like the astronauts around the space station. The astronauts around the space station are not so far away that they don't feel the Earth's gravitational pull. They're falling, actually. They're just falling all the time. If anyone watched Jeff Bezos's flights where they did zero gravity flights, it's literally no different than this. They didn't have to go high up. They could have just jumped off a building. And you would have experienced the same thing with a very unhappy ending, obviously. So that's the first idea. Einstein calls this happiest thought. The second observation is simple. Nothing, when it falls freely, travels on a straight line around the Earth. If I throw something around the Earth, we all know it follows a curve. So he puts these two ideas together and he says, the experience of gravity is falling freely along curves in space. And what the Earth is doing is it's curving space-time. It's really an enormous leap. He didn't get to it by mathematics. He got to it by intuition. And then he struggled to mathematically express that intuition. Now, shortly, here's my space station painting from Leah. So the International Space Station is falling along a natural curve around the Earth created by the Earth's mass deforming the shape of space-time, and the space station is actually falling all the time. Once it got up there, they turned off the engines. It's going at 17,500 miles an hour, I believe is the number, and it's got no engine firing. It has to fire occasionally because it has to stay in that orbit. But what it's doing is it's falling so fast that it always clears the horizon and never crashes into the Earth's surface. But they are absolutely within the gravitational pull of the Earth. And the reason why they look weightless is because they are basically performing the plane experiment, but with a better outcome. And of course, we know if you want to escape from the Earth, like SpaceX is trying to do, if you've been watching these rocket flights, you have to travel at 11 kilometers per second to break out of the Earth's gravitational field, but then you can freely float away. Now, very soon after Einstein first published in 1916 his general theory of relativity, which is the mathematization of this idea of a curved spacetime, he gets a letter from a friend on the Russian front who had enlisted during the war, World War I, who says, he says something absolutely insane, like, the war has treated me kindly enough. I have had the pleasure of wandering through the land of your ideas. And he sends him this description of a thought experiment. He says, imagine that instead of the Earth and the curved spacetime around the Earth, or the sun and the curved spacetime around the sun, I crushed the mass of an entire star to a point. He didn't ask how this could happen. He never thought it could actually happen in nature. He just said, imagine. And then he wrote down the description of the curved spacetime around this point of a crushed star. And the fascinating discovery he made was that in order to escape from that crushed object, you wouldn't be able to go 11 kilometers per second. You would have to go faster than the speed of light. And since nothing can go faster than the speed of light, that object would simply go dark, because not even light could break away from the curves in spacetime. They didn't call it a black hole, and Einstein was very impressed with this math and description, but he believed that nature would protect us from their formation. I mean, after all, it's quite absurd to imagine crushing a star to a point. There's no reason to believe that that would at all be possible. If you were to, space-time is not helpfully painted with the curves showing you where they go. If you were to be around this crushed star, this is all that you would see. Nothing, darkness against the darkness of space. You can see a black hole if you illuminate it helpfully, just like you can see the shadow of a tree. To cast the shadow of a tree, you need a source of light. And with the black hole, you can put hot, bright light around it and illuminate it, and anything that gets too close, a region we call the event horizon, will not be able to escape because it cannot travel faster than the speed of light, and it will create and cast a shadow right there. So the only thing that there is to see is the shadow of the black hole. And one thing I would like to do tonight is to kind of shuck away some of the misimpressions of black holes. And one of them is that a black hole is a thing. We'll talk about this more, but in some sense, a black hole is an empty region of space. There's simply nothing there. It's a shadow. Now, if we were to try to make the sun a black hole, which we can't do, but some evil future civilization comes and tries to crush our sun into a black hole, our entire sun, which is now 1.5 million kilometers across, would be crushed to 6 kilometers across or less, city size. So one of the things about black holes is that they're hefty, but they're really small. Black holes are tiny. Imagine the heft of the sun, but it fits in New York City. And this is a mathematical model. It's not a cartoon. It's actually a formal mathematical model. Andrew Hamilton, the physicist, he did this. Imagine putting a bright source of light behind this imaginary collapsed sun, so you can see the shadow. All that's happening with the shadow is that any light that's getting within that 6-kilometer region of the event horizon is lost inside, cannot escape, so that whole region goes dark. He's imagined a little Earth orbiting this black hole, and the Earth is not actually being deformed. If our sun were to turn into a black hole tomorrow, our orbit would be fine. And this is also one of the myths, that black holes are these vacuums of destruction and mayhem. Actually, our orbit would be just fine. We would stay in orbit where we are. I mean, it would be apocalyptically, cold and dark, and that would be very grim, but the orbit is fine. Black holes, we're safe from black holes at a safe distance. They're actually quite benign. You don't bug them, they won't bug you. So in this, what's happening with the Earth is it's simply that the light is also trapped by the black hole, and it's making it like a lens. so that any image, as you can see, even as the Earth passes behind it, we can see it as though the entire space is itself a lens, showing us the Earth. Now, for decades, people thought that this was a fascinating mathematical model, but that it would never exist in nature. Did anybody see Oppenheimer? Yeah. So Oppenheimer's most important contribution to theoretical physics came around this topic, and even he didn't really live to understand the significance. In 1939, he wrote a paper with a student. It's vaguely referenced in the movie. There's a small kind of toss-off mention of, oh, your paper just got published, but it was also the day that the Nazis advanced on Poland. And their paper was lost for many years. It just was not what was on people's minds, to say the least, even Oppenheimer's. But what they were working on was trying to understand nuclear physics. And a lot of that nuclear physics is precisely what went into building bombs and building weaponry. And so a lot of the same minds that were engaged in the Manhattan Project and in the ambition to win this arms race, essentially, we're also quite agnostic about nature in the sense that the same nuclear physics could be applied to understanding how stars shine. Essentially, our star is a thermonuclear bomb churning earthfuls of thermonuclear material in these core nuclear reactors. And Oppenheimer's paper was this study of what would happen if at the end of a star's life cycle, when it ran out of fuel, and a lot of the core would sort of suddenly cool and it would explode in a supernova, many of them, not all of them, and if the core that remained was heavy enough, then it would begin to collapse under its own weight. And the argument, it was believed, and I think quite reasonably, that for sure matter would resist catastrophic collapse. But Oppenheimer really did show that even nuclear forces, the unbelievable nuclear power that goes into the release of this kind of power and energy, could not resist the overwhelming unhindered gravitational collapse if the core was heavy enough, several times the mass of our sun. And they argued that a black hole would form, that nature had thought of a way to make black holes, and that was to kill off some very massive stars. At that time, a lot of his ideas were rejected. I think he took that quite bitterly, but before even the term black holes were coined, Oppenheimer died and never lived really to see the impact of this research, that even those who fought him on it came to the conclusion that, in fact, black holes are the inevitable death state of very heavy stars, which is quite unbelievable. Now, the peculiar thing about black holes is, well, they're very hard to see. Imagine something 6 kilometers across, lost in this galaxy, and it's dark. They're actually incredibly hard to see. This is another mathematical model. Imagine you're a space traveler, you go a few thousand light years away, which we can't yet do, and you encounter this shadow on your field of view, and you were not paying attention, you did not read the survival guide, and so you just cross right into it. Now, the stunning thing in this horizon, this shadow, there really is nothing there. That star, when it collapses, when it gets to be a few kilometers across, it reaches the point where not even light can escape. It's as though it's inscribed the event horizon in the shape of space-time. But the star itself, it continues to fall. It can no more sit there than it can race outward at the speed of light. So the star continues to fall, and where it goes, we definitely do not know. But we know it cannot be there at the horizon. It's gone. There's lots of arguments for what happens to it, and we can talk about all of those. It's actually one of the most fascinating forefronts of scientific research is trying to understand where did everything go. But we know it's not there at the event horizon. So if you were to cross into the shadow, it would be no more dramatic than stepping into the shadow of a tree. There's nothing there. So a black hole is really nothingness. It's empty space-time. Another peculiar thing about black holes is that they can be bright on the inside, even if they're dark on the outside, because as you fall in, this is one of the mathematical models, the light from the entire galaxy can catch up to you and shine behind you. And as you get crunched closer and closer to this sort of catastrophic, where the curves in space-time are so unwieldy that you yourself become crushed and torn to bits, what Neil deGrasse Tyson famously and somewhat regrettably calls spaghettification, you will see all of this light come in behind you, and it will be like this flash of bright light, a kind of near-death experience, but I often call it a pretty total death experience. But the idea is that black holes dark on the outside, but they can be bright on the inside. And they really are the most peculiar astrophysical phenomena. Now, I try to convey that they're hefty, but they're small. And so imagine trying to observe a teeny tiny 6-kilometer across black hole at thousands or hundreds of thousands or millions of light years away. It's incredibly challenging. And until very recently, we had never seen a black hole. Until 2019. We had never seen a black hole. We had seen indirect evidence of black holes. We had seen mayhem and destruction of black holes tearing things apart, and bright signatures of stars being cannibalized by black hole neighbors, but we had never seen the black hole itself. And if you think about it, how could you possibly see such a tiny dark thing? But there was this one possibility that scientists began to pursue, and that was supermassive black holes. Now, we don't know where they come from, but we know that they exist. They're black holes millions or billions or even trillions of times the mass of the sun. And they lurk, for instance, in our own galaxy. If you look at the Milky Way and you look in the direction of the constellation Sagittarius, there's an object we call Sagittarius A star, and it's been observed by looking at stars orbiting in the absolutely empty center of our galaxy. That's 26,000 light years away from us. And we see these stars, astronomers observed these stars orbiting for 15 years, 20 years, 25 years, and they concluded that they're orbiting a very compact, extremely massive object, 4 million times the mass of the sun. 4 million times the mass of the sun. And they deduced it was a black hole. Now, if you imagine this very heavy object, it's only 20 times the width of the sun. If you can imagine the sun on the sky, and you picture 20 times the width of that, you imagine 4 million times the mass jammed in there, and now you push it to 26,000 light years away. That object, from our point of view, in the sky is smaller than a piece of fruit on the moon. It's an insane project to try to take a picture of this black hole. The project is called Event Horizon Telescope. Did anyone see the picture when it finally came out? Yeah, okay, awesome. I'm going to show it to you again. So I went out to the National Press Club when the announcement was made, and the only big surprise was that they had observed it was all a huge surprise, but if they're making a press announcement, we knew what they were going to show us, right? Was that there was one other object in the entire sky that was about the same size that's a black hole, and that's a completely different galaxy called M87. It's 55 million light years away, much further away. It's a different galaxy, but it has a black hole over 6 billion times the mass of the sun. It's enormous. It's about the size of a solar system. But at 55 million light years away, it's also about the size of a piece of fruit on the moon. And they made a coordinated telescope, giant telescope, by stringing together and coordinating radio telescopes all over the globe so that there was one giant telescope, essentially the size of the Earth, working like a coordinated single image to capture this stunning picture, which is the first picture humanity has ever taken of the actual event horizon of a black hole. And then just a couple years later, they similarly went back to reanalyze and look at our own black hole, Sagittarius A star, the one in the Milky Way, and in fact were able to return a picture of our own black hole. It really was quite stunning, and it was exactly what we predicted it would look like, but really to emphasize the idea that what we're really seeing is the bright light and the energy around this shadow, and that there's really, it's a picture of nothing, but an empty space. You know, I don't have a timepiece, and I think I talked really quickly, but I'm just gonna go for it. And then we'll do a long Q&A. Okay, I'm not ready yet. Not ready yet. Another remarkable thing that we've come to understand is when we look out, this is the Hubble Deep Field from the famed Hubble Space Telescope, which is looking at a dark patch of the sky. In fact, when the director of the Hubble Space Telescope told people he was just going to point this incredibly valuable instrument where people were fighting to get time to look at things, he was going to point it at an empty part of the sky where we saw nothing, and it looked dark. And he was just going to stare at it with the Hubble Space Telescope for a few days. And what it returned was in this tiny patch of sky, it's about a tenth the size of the moon on the sky, that there were thousands, tens of thousands of galaxies in it. And that was our first understanding that the universe is absolutely replete with galaxies, and that this wasn't the same part of the discovery, but that every one of those galaxies we now understand, we believe very nearly everyone, has a supermassive black hole at its center. And those black holes are somehow, we don't know where they come from. They are not dead stars. They may have formed in the very early universe, skipping stars altogether, directly collapsed in the primordial early universe. But we have no idea how they got so big. But we do know that they seem to be playing a fundamental role in sculpting galaxies, because they're there in every one of them. And that they may play a role in shaping parts of the galaxy so that it's habitable, so that there are regions that are the seeds for life, like our own solar system. So black holes are in some sense fundamental to the emergence of life in some subtle way we can't yet piece together, but we understand that they are part of our fundamental history. And we are orbiting that black hole as an entire solar system together, as surely as the Earth orbits the sun. And I think the most remarkable thing to imagine is all of this work that we do to understand the universe, all of this light that we collect over the history of humanity coming from billions of light years away, all of it, and all of us, and all of our atoms, and the remnants of our solar system when our star dies, all of that may very well end up in that black hole, because we are slowly spiraling in. So black holes aren't just our past, they're very likely our future. And everything that can will in the universe fall into black holes until that's really all that's left. And we can imagine, I always say the future is a lot longer than the past, a far future where everything that can has fallen into black holes. The black holes themselves finally go completely dark and eventually just evaporate into oblivion. Thank you so much. Oh, my screen went dark, sorry. Excellent, this is my favorite part. Can we do a Q&A? I think there's microphones somewhere. Don't be shy. Well, the question was, what is it like in a black hole? So if you cross into the shadow unknowingly, didn't realize what you had done, there would be nothing there. It would be an undramatic experience of just like stepping into the shadow of a tree. But if it was a black hole the size of a star, a dead star, you would have fractions of a second before all the curves in space-time drove you towards what we call the singularity. Literally, your feet would be pulled more than your head, presuming you went in that direction, and you would find yourself eventually torn to shreds, literally by the structure of the space-time itself, pulverized and ripped apart into your fundamental quantum particles. It's not a very happy experience, but then we don't know what happens. And some people suggest that maybe all of those fundamental particles actually traverse into a Big Bang. Black holes also, by the way, are bigger on the inside than they are on the outside. It's like Doctor Who's TARDIS. You know, you go inside and it's this huge thing. They can be 6 kilometers across on the outside, but literally as big as a universe on the inside, and because space-time is really tricky that way. So it is conceivable, people have argued, that there's a black hole that goes into a white hole and an entire Big Bang is on the other side. And so all of your particles could start again in a new ecosystem and find new life and reemerge in a new Big Bang and a new universe and end up in a planet or a tree or a person or something. There's a lot of people who think that that's absolutely not going to happen, and there's lots of very technical reasons why, and they think that there are instead much more reasonable quantum wormholes connecting the black hole from the inside to the outside, and that actually all your particles will come back out again. People heard of Stephen Hawking, famous scientist Stephen Hawking. He was real provocative person, really enjoyed causing a bit of a kerfuffle occasionally, and what he became famous for when he was a very young scientist was the observation that even though I've said black holes are the darkest phenomenon in the universe conceivable, he realized that there was a very subtle quantum way that black holes could actually evaporate. And people have still not been able to reconcile how those two things are possible. But everyone knows he's right. And so the debate has been going on since 1974. And it is really a crucial debate because if we understand, there very well may be quantum wormholes connecting the inside to the outside, and that's how black holes evaporate, it will change our entire understanding of quantum gravity and the laws of physics. So that's the terrain where everyone tries to understand what's beyond Einstein, is by understanding that very question. There is somebody at the mic here. Yes, please.
Hi, wonderful presentation, thank you. But I'm confused about a nuance here.
Yeah.
You said earlier that an orbit around a black hole is inherently stable, but then you said that we're all going to plunge into a black hole.
Right, yeah.
Could you clarify that a little bit for me?
Absolutely. So there are stable orbits around a black hole as long as you stay outside the event horizon, but it's actually, you can get really close in. So let's say a black hole is 6 kilometers across. There's a stable orbit at about 10 kilometers where you could take a circle. I mean, that's right up against the black hole. Now, you can't get that close to the sun, right, without being incinerated. But there's this phenomenon called gravitational waves, which you might have heard of. And as we orbit, even the sun, we're losing a little bit of orbital energy, actually rippling, causing ripples in the actual shape of space-time. So if you imagine you're free-falling along a curve, as we orbit, the sun wobbles a little, and as it wobbles, those curves have to readjust around the sun. Literally creates a wave in the shape of space-time. And those gravitational waves, very subtle, also are argued about for decades, carry away energy so that we slowly spiral in. It's very slowly. We detected the gravitational waves from the collision of two black holes in like 2015. It was. Do you want to see that one? Okay. I had that in here, but I cut it out. It's really cool. So let's do that. So a Nobel Prize. Oops, I have to unskip it. Forgive me. Okay. So a Nobel Prize was awarded for this discovery rightly. It took 50 years. So this is a numerical simulation of the actual detection. There are two black holes, 30 times the mass of the sun each, roughly. They were well over basically 1.5 billion, let's call it, light years away. And they had orbited each other for, could have been billions of years, losing energy to these gravitational waves until the final fraction of a second of their lives together. This is drastically slowed down so we can see it. They're orbiting near the speed of light. In a fraction of a millisecond, the black holes merge. The gravitational waves get really big. You can't see them. It's not light. And they ring out through the universe. They travel for 1.5 billion years until they, multicellular organisms are just differentiating on the Earth when they left their location, literally ringing space-time like a drum, but you can't see them. They wash over this very subtle experiment that was built in the US. There was one instrument in Louisiana, one in Washington State, and the instrument picks up the ringing of space kind of like a musical instrument, like an electric guitar almost, and it records the ringing. It's a 4-kilometer-long instrument. It's a whole long story. And then it washes past Louisiana, and it rings the instrument in Washington State. And after 50 years of working on it, they recorded the first time. It's literally a sound. I can play it for you. We'll play the sound. It's literally like recording a ringing drum and playing it back in the human auditory range. So I'll play for you what they detected. It happened very fast. In a fraction of a millisecond. Here it comes. That's it. That was it. Didn't you expect something, I don't know, more baritone?
Is that available as a ringtone?
That's what I thought its largest effect in humanity would be, the ringtone. I haven't really heard anyone using it yet. I have seen people tattoo it on their arms, no exaggeration. The shape of the waveform as it was recorded. And that little bleep, we call it a chirp, was very thoroughly predicted over the decades. We never knew if black holes would actually be plentiful enough in the universe for us to detect it until that event happened. And as silly as it sounds, that little chirp, it was the most powerful event detected since the Big Bang. And more power came out in the ringing of the shape of space-time than all the power in all the stars in the observable universe combined. It's quite amazing. And the thing is that gravity is incredibly weak. And so by the time it gets to us over 1 billion years later, it certainly can't ring our ears, but if you were nearby floating in empty space, it is conceivable it would ring your eardrum, the squeezing and the stretching of the space, and you would actually hear that. And then you should get out. Move on. Thank you for your question, though. But anyway, the point was to say you lose energy to those, and then you spiral in. And so it'll take a very, very, very long time. Don't worry, the sun will blow up first, before that. Yes?
Yeah, thank you. It seems like that these black holes will be gobbling up matter at incredible rates. About what fraction of the universe would you say mass is contained inside black holes, and at about what rate are black holes eating up the mass around them?
Yeah, it's a great question. For a while, people wondered, could the dark matter, which we can't see, can't identify, but we can tell is out there just from gravity, just from the effects it has, be tied up in black holes? And so far, I think the answer is probably no, but it's not a definitive no. The thing is black holes don't gobble up things at an incredible rate because, again, even if our sun were to become a black hole, it wouldn't gobble us up. It would take us every bit as long to fall in as it will take us to fall into the sun. And so, they're really safe from a safe distance. They're no different than a planet or a star. As long as you're even a little bit far away, you have to get really, really, really close to a black hole to get into trouble, at least from the gravity. So even our own black hole at the center of our galaxy was gobbling up a lot of stuff quite a long time ago and was probably shooting out powerful jets and was a very energetic system. And those jets, which have to do with spinning up magnetic fields, and it's not matter coming from inside the black hole, it's just churning up matter around it, causing mayhem, all of that quiets down. And so our black hole is pretty quiescent. But those jets and all that early activity might sculpt the size of the galaxy, clear out certain regions, allowing planets to form in quiet regions. And again, that's a way in which it could have an effect on creating a habitable solar system. But about 1 billion black holes in our Milky Way, probably, by the end of their life cycle. So it's a lot, but it's not enough to, it's still not the max, it's not the most mass, right? Most of the mass is still in stars. Yes, hi.
Hello. The neighboring galaxy, Andromeda Galaxy,
Yeah.
is on a collision course with us, the Milky Way galaxy.
Yeah.
Do you think the two supermassive black holes in the center of our galaxies will collide?
Oh, I love that question. I think yes. So around, our sun will probably end its life cycle first in a few billion years. And when it does, it won't become a black hole. It's not heavy enough. It'll just kind of bloat and distend. It'll vaporize the inner planets. Astronomy is full of good news and optimism. But very around that time, maybe within 1 billion years of that time, we will collide with Andromeda, which is a neighboring galaxy. And it does have a supermassive black hole. And we do think that the black holes will merge, much like what I just showed you in that mathematical simulation. And those two black holes will become a new black hole. So strictly speaking, we'll fall into that black hole. Our entire solar system could actually survive the collision because it's mostly empty space between the stars. And it very well may be that with our distended star, the vaporized planets, but basically all our matter, all the information we've put out into the world, Voyager and all those things will likely come with us as we orbit that new black hole. Absolutely. I don't know if it's been given a name yet. But that is for sure in our future. Yes, please. Do you want to ask at the mic? You can just ask. Sorry? Tell me, what did, say it again? Milkdromeda. I don't know. It was a friend of yours? Yeah. I don't know, but I like it. I heard somebody called Gargantua. I mean, I don't know if any of them have. When does a name stick? I don't know, but I'll look it up. Thank you. Yes, please.
Hi, so I have a small question. So you mentioned that everything will collapse around the center, that the black hole that's at the center of our galaxy. Mm-hmm. But alternatively, if the black hole keeps getting smaller and smaller, the event horizon will shrink as well, and then therefore lose its influence around it. And so the matter around it will probably not collapse and instead just float away.
So if I have your question correct, you're saying because of Hawking's mathematical discovery that black holes will evaporate, eventually the event horizon will actually get smaller.
Right.
And therefore less influential. And I think that's completely true. However, it's a staggeringly slow process. And so when we look at black holes, they are, I don't even know the number, I don't have a name for how far in the future we could even begin to notice that they are, through Hawking's process, evaporating. So the black holes will be stable for a very, very, very long time before they begin to evaporate. So it's true, it may not go exactly as we're describing. There's dark energy pushing everything away. There might be one black hole in an entire observable universe because everything's expanded away so far. And maybe stuff will get stretched away and never meet the black hole. All of those things are possible. So it is just it's a game of a competition of timescales and what lasts longer, and we don't know exactly all those things. Dark energy could turn off, and black holes will have all the time in the world to slowly consume everything that can possibly fall into them, and they will certainly grow faster, presumably, than they'll evaporate. The evaporation is so slow. The heavier the black hole, the cooler it is. the slower it evaporates. So it's only the final stage of the black hole that it goes off like an explosion. And we think that primordial black holes could have formed in the very early universe. And the smaller they are, the hotter they are, the faster they evaporate. So we believe that those just flew off like firecrackers and are gone.
Great, that's helpful. Thank you.
Thank you. Maybe one more question if there is one? Yes, thank you.
So, I'm only an artist, so I don't know. And so pardon my language. So there's a two-dimensional representation, of the space-time that's bending down, right, into this infinite point. But how can it bend? My problem, mentally, is like, how can it bend down in space?
What does down mean?
Because,
Which direction's down?
So when you flip that up,
Yeah.
the reverse is going in.
Right.
And so it's like infinitely coming into the center versus, so like the fiction of that image being like a poor representation of the actual kind of physics going on. And is there a better image?
Yeah, it's an
that
excellent
kind of
question.
civilians can digest that represents the kind of multidimensionality of that gravitational point?
Yeah, so none of us, even my most famed mathematician friends who study hyperbolic higher dimensional geometries, are capable of actually visualizing higher dimensional spaces. Visualizing. And as an artist, I really do appreciate that. What that drawing is, that classic drawing, which I even showed a painting of those lines going into a funnel, it's technically called an embedding diagram. It is not really three-dimensional space. One of those dimensions is actually plotting the curvature of space-time. So it's very misleading. I often don't use it because of that. So there is no real down. It's not even a fiction. I can mathematically show my students how to make that diagram mathematically accurately, but what you're really doing to visualize it is you're embedding in a higher dimensional space, and then you're suppressing a bunch of spatial dimensions because no one can visualize it. So it's a bit of a cheat. It really is. If you ask what is a better way to visualize, so in that sense, what it's representing is how strong the curves become, and they become that strong in every single direction as you go inward. And we just can't visualize. What we really want is a four-dimensional view of the three-dimensional space-time, and then the fourth direction, the strength of the curvature, but our brains can't do it. So we suppress a bunch of dimensions, keep the curvature. So there is no down. You're absolutely right. It's actually doing that in every direction. And I just can't visualize it beyond that because it's one dimension too many. But yes, embedding diagrams are fascinating and they're accurate. They're just not three space dimensions. You're not looking at a three-dimensional space. But since you asked that question, I want to point to this magazine that we work on at PioneerWorks, which was mentioned, which is an artist cultural center where I'm director of sciences, and we talk about things like that. How do you visualize? There's one of our series, so the magazine's called PioneerWorks Broadcast, and we cover art, music, science, technology. Maybe you noticed from working with that artist, Leah, I love working with artists. It's one of my favorite things to do, and because I think about these questions, and it's not just about visual representations, but it's about what moves us? Why do we find these things interesting? Why do we use language and math and all these things combined? Why does it take all of it to really understand? It's not enough just to do math. It's not enough just to do the language. It's not enough to just visualize it. It's part of a composite of how we try to understand the world and our place in the world. And one of the series that we publish is called Picture This, where we ask a scientist to use a formal drawing, so it's not an artist's representation, and to explain how they read this drawing as a mathematical object. So one of the first piece I wrote on Penrose, Roger Penrose, who won the Nobel Prize, Hawking's peer and close collaborator, about his proof, a mathematical drawing that black holes were the inevitable outcome of the collapse of stars. So it's short. I hope you'll take a look. Thank you so much, everybody. You've been wonderful hosts. Thank you.